Good morning to all. Today we are discussing the next topic of the stereochemistry, that is the concept of the stainless string. In the last class we have discussed the um, Bayes strain theory. According to Bayes strain theory, the cyclohexane is highly unstable. That is the demerit of the Bayes strain theory. So according to Bayes strain theory, the cyclohexane has a bond angle of the 120 and it is deviating from the tetrahedral bond angle 109.5 degree. That's why cyclohexane is a highly strained system. But actually it is a stable system. Cyclohexane is a stable molecule. How we will explain the stability of the cyclohexane? So Sachet and Moore proposed that the cyclohexane is a strainless string, and according to this theory, they had proposed their theory in 1890. According to their theory, the carbon atom of the cyclohexane and higher alkanes are not planar, but they assume strain-free Packard configuration in which each of the carbon retain its normal tetrahedral bond angle of the 109.5 degree. So Sachet constructed two models of the cyclohexane and which is called board form and the chair form. So according to them, this board form and chair form are devoid of angular strain and torsional strain and steric strain, and the and it is a non-planar molecule. According to Sachet and Moore, the cyclohexane are devoid of angular strain, torsion strain and steric strain, and it is a non-planar molecule. Now we will discuss in detail the Sachet and Moore theory. So according to their theory, the cyclohexane and other higher cyclic hydrocarbons are exist in a non-planar molecule and they acquire the Packard ring structure, and they are not a non-planar. That's why it acquire the tetrahedral bond angle of the 109.5 degree. So the higher molecule are stable. Now we are moving into the cyclohexane in detail. In cyclohexane, the molecular formula of the cyclohexane is 6,6H12, and there are four different conformations possible. The stable conformations of the cyclohexane are the four different type. First one is the chair form, second one is the board form, the third one is the half chair, and the fourth one is the twisted board form. Now we are moving into the individual conformation of the cyclohexane in detail. See here, this is the first one is the chair form of the cyclohexane. As you know that the most stable conformation of the cyclohexane is the chair form. Now, how we will represent the chair form? The individual representation, that is the first representation and its Newman representation is very important for university examination. So we have to start from 1. Here this is the 1 and we have to move into 2, and the 1-2 bond, CC sigma bond is tilted, and 2-3 bond is in the downward, and again up 3-4 bond is again upward, then downward 5, then upward 6. So this is the cyclohexane structure. While we are observing this molecule, we have to observe this molecule towards 1 and 6. So if we observe towards 1, we cannot see the 2. So first of all, first carbon atom is represented by a dot, and the back carbon atom, that is the C2, is represented by a circle. Then C2 is connected to the third carbon atom, C3, and that is in the downward plane. That's why it is written in the downward of the plane. And next is the fourth one is if you are observing the same molecule towards 6 and the 6 is in the upward and 5 is in the direction of the observer, so 5 is in the front and the fourth is in the backward and the 6 is in the upward. So this is the Newman representation of the cyclohexane. So the bottom of the slide represent the boat form of the cyclohexane. Everybody know the shape of a boat and it is very simple to draw this boat form. So in the boat form, while we are writing the boat form in terms of the Newman projection formula, we have to observe the molecule towards 1 and 5. That is in the same manner of the chair form. So we cannot see the carbon 2, C2 and C4. So first of all we have to draw the C1 that is represented by a dot. Then back carbon atom C2 and C4 is represented by a circle. And the 6 carbon number C6 and C3 are in the upward, so which are in the eclipsed form. So we have to draw like this. Okay, this is the Newman projection of the boat form. This is also very important. Now we are moving into the relative stability of the chair form and the boat form. We already studied that the chair form is the most stable conformation of the cyclohexane. I am already told you that the cyclohexane acquire the tetrahedral bond angle of the 109.5 degree. That's why both the chair and the boat form are devoid of angular strain. Now in the chair form we can see this two carbon atom. Here the the C3 and C6 are in the different plane. C3 in the below the plane and C6 are upward the plane. See here the chair form, one of the end of the chair form is in the upward and the other end of the chair form is in the downward of the plane. So these two ends are maximum distance apart. That's why they are devoid of torsion strain. And here also we can see that the hydrogen atom attached to the end of the chair form are the maximum distance apart in the chair form. That's why the chair form are devoid of the steric strain. So since the chair form is devoid of the torsion strain, angular strain and steric strain, it is more stable. And next we are coming into the board form. So in the board form, as we discussed, the board form also devoid of the angular strain since it acquired the bond angle of the 109.5 degree of the tetrahedral bond angle. And the adjacent carbon atom in the board form I have written in the red color arrow, red colored line, and which are just behind the other. If you are observing the molecule in the sidewise in the right hand side, the first carbon atom, that is which is shown by the red line, it is just behind the other carbon atom. That's why these two carbon atom are in the eclipsed form. Since they are in eclipse, the board form acquire the torsion strain. And we can see the red color line, and this is a hydrogen atom, CH sigma bond, and this hydrogen atom is known as the flagpole hydrogen. You know that for every boat or boat there they will have their own flag. So these two hydrogen is representing the flag of a boat form. That's why this hydrogen is known as the flagpole hydrogen. And since these four flagpole hydrogen are very close to each other, it acquired the steric strain. So that's why the boat form acquire the torsion strain and steric strain. That's why the boat form are the less stable than that of the chair form. But these two forms are the chair form and board form are interconvertible since the energy barrier between the board form and chair form is very less. That's why it cannot be separable at room temperature, and it is interconvertible. Chair form and the board form are the interconvertible one. Now we are moving into the axial and equatorial bonds. So in the chair form or in cyclohexane, we can see the 12 CH sigma bonds. But some of the CH sigma bond are aligned in the axis of this cyclohexane. I have shown the axis here in the dotted line, and the CH sigma bond are written by A and E. So the every CHAs are which is parallel to the axis of the cyclohexane. So these hydrogen atoms or CH bonds are known as axial bonds. And here we can see that some of the CH sigma bond is written by E. This that is the CH sigma bond which is represented by ER lie in the equator of the ring. So that's why these bonds are known as equatorial bonds. So in cyclohexane we can see 6 CH axial bonds. I have written this axial bond as A. Here we can see that the 6 axial bonds which are in the upward direction and is parallel to the axis of the cyclohexane. And we can also see the 6 equatorial bond, and this equatorial bond are situated in the equator of the cyclohexane. So this is very important. So these are the conformation of the cyclohexane. I hope that you understood the concept. Thank you.